Lee, welcome on the podcast.
It's good to be with you.
So tell me, we're obviously going to talk about your paper in Nature. What's your background? How did you get to this research?
Um, I suppose I remember wanting to be a scientist and being confused by the entire concept when I was a kid, and I was always fascinated how things worked. And I suppose whether it was electronic things or the cracks I would find on the pavement, diffracting light through marbles, or looking at things growing. And then I guess when I was always going to become a scientist. And for certain reasons, I ended up becoming a chemist. And I find chemistry so fascinating because it was utterly confusing, but not because it was just indecipherable, but because people would basically put labels on things and not ask why. So that was kind of interesting. I really enjoyed doing my degree and asking questions, and I became an inorganic chemist in my PhD, where you have this big thing called the periodic table, and there's one little element, carbon, which seems to be ring fixed for organic chemistry. So if you want to be a real chemist, I'm just joking, right? But it's almost like the difference between a doctor and a vet. I was saying this the other day. So if you're a vet, you have to know all the animals. And as an inorganic chemist, you have to know all the periodic table. But if you want to be a really good doctor, you have just to know humans. And I think carbon is where the organic chemists play, and they're really good at that. And so I found that tickled me pink. And then I did a PhD in bioinorganic chemistry, which is basically looking at things called proteins, which you find in obviously in the cells that do, the machines that do things. And in this case, the protein would have a metal in it. And I was fascinated with that and crystal structures and 3D stuff. And I wrote some code and did experiments. And then when I found myself as a lecturer, becoming a professor, I'd always been interested in chaos theory and complexity since I was a kid. And it gave me the chance to start saying, well, the ultimate place where complexity is born is in chemistry. And that's kind of my history. And I always wanted to ask, what is it that makes chemistry complicated, and what does that mean? And then it's kind of left me on a path to consider in the last few years the entire field of complexity science is founded on one thing, but applied in the wrong place. And I'm trying to reapply it or redefine it in chemistry and apply it where it should be. And that's actually causing quite a few to and fro's, and we can go into that in detail. And I think I actually now understand why people have been gatekeeping, right, in between these two fields, well, many different fields. And that's kind of how I got there.
So what do you mean? Just touch on that. What do you mean by applying it in this different field? What do you mean by that?
So classic complexity science was born out of computing and mathematics and what was doable. So people talk a lot about what class of problem does this algorithm fall into, right? To basically say, well, how big does my computer need to be? How much time do I need? And so people then applied complexity from computer science outward, right? So there's an idea and they then applied this to biology and physical phenomena. And I realized, actually, probably when I was 17 years old, when I was looking at chaos theory, this is all wrong. The universe isn't a computer, and I know lots of people think it is, and their ontology is that. It's like it simply isn't. And what I mean by that is we live in a universe that isn't a CPU and RAM, right? There's stuff moving around. And so I wanted to ask myself, but stuff is complicated, and there is complexity. So how do we start to explore that in a rather different way? Because if what you do is you start to try and put everything into whether it's a program or not, it kind of removes some of the fundamental understanding. And what that means is we've built mathematical models of the universe on complexity that we can simulate, but is not testable or instantiatable in the universe. And they should assume the universe is a computer or a simulation. Now then, when you get into that, we're getting to this really quickly, only 2 minutes in.
It's great.
If you believe the universe is a simulation, that's non-falsifiable. Then basically that's a set of religious like beliefs. And as a scientist, although I may or may not have beliefs, I don't work in areas that require belief at the base. So when someone says to me, "Oh, I'm a simulationist," I'm like, "Sure. Well, you could be a Catholic as well. You could be a Muslim. You could be whatever. But that's great. Well done, being Buddhist, Catholic, Muslim, religious. Let's park that and let's discuss the universe." And that kind of makes them divide by zero because they think that the simulation or a hypothesis or something is a defendable thing. Now, bring that into complexity. Why am I saying that? Well, if the universe is not a computer, then we need to redefine what we mean by complexity and work from there. And that's where I started. It's like saying, my gosh, the field is complicated. It's like 50 years of complexity. I actually sent an email to a very, very interesting academic. I don't even think he had a PhD, and that was Freeman Dyson. And I was talking to Freeman about one thing, and I happened to tell him about my work on complexity, and he went, "Please, Dr. Cronin, do not work on complexity. People have been working in complexity science for 50 years and got nowhere just because it's meaningless." And I think he was actually saying something similar. It's not meaningless, but it's complicated. So yeah. So I wanted to start again with complexity. I want to be respectful of computer science because complexity means something in computer science when you look talking about algorithms and resources. But I wanted to understand the universe, biology, evolution, and chemistry, and that doesn't fit into computability. That fits into something else. And the fact that people have been forcing it to be in this computational complexity science has actually stopped us from making progress and asking what the phenomena of life is. And that's why I kind of got there.
So are you saying that you're taking complexity ideas and you're bringing it back to chemistry, but you're not letting, shall we say, the dogma of complexity? It's more a set of tools you can use to understand the chemistry. Have I got that right?
No, I'm even more radical. I'm saying that complexity science is meaningless outside of computer science.
Okay.
And we have to completely meaningless.
Yep.
And we actually have to start again.
Okay.
So that even chaos theory, that was really, sensitive depends on initial conditions and all that stuff is cool, but again, have to start again. So even when you say the weather is a complex system, that is correct, but using the tools of complexity science to explain the weather is not correct. It doesn't work. So I'm saying the entire paradigm needs to be redone. I'm being actually very concrete. And I mean, one would argue controversial, but it's not, because it's like, I'm not saying that people doing complexity science are bad. I'm just saying don't try and apply complexity science measures to things that aren't in a computer, because then you're going to need a computer in the system. Don't compare how a seed is evolved to a computer program unless you're sure the seed is running in a computer.
I mean, it's interesting. I was talking to Kevin Mitchell recently, who wrote a book, Free Agents, and ended up talking about evolution as part of that. And we're talking about, evolution deciding what's successful or not. And as he was making the point that, of course, evolution doesn't decide anything. This is just happening. And with sort of hindsight, we call it evolution, that's what explains what has happened. I mean, it sort of feels you're saying something similar here, and he's going right back to, let's just look at how things are selecting and moving through, and then evolution is the sort of what we can look at and see and say, yes, that's clearly evolution. But trying to use sort of evolution as a building block to understand, things like free will is very, very difficult to do.
I know. I think you can use evolution to understand free will. I think we can do that. I think we should start at the bottom. Starting at the bottom is just saying, I would make the argument that the universe, without selection, it has no real complexity in it. It's complex in that it has lots of moving parts, but there's nothing mysterious about them. And there is maybe physical emergence.
Yep.
But I would argue at the base to say if we imagine a universe, let's almost just imagine the point before the Big Bang.
Yep.
There was nothing. Let's argue there's nothing. There may be time, but that's arguable. And then suddenly there is a singularity in which there is all this energy produced. So suddenly you have a huge amount of energy. Presumably that's isotropic. So it's spherical. You've got this there, and it's just expanding. So there's space.
Mm-hmm.
That's really simple, right? There's nothing much. I mean, the photons in that are have no idea what to do, other than at some point start to crystallize. So what that means, the photons transform from being energy and produce particles. Now, when you get particles, you get interactions, because photons find it really hard to interact with one another. When you start to get particles, mass, they interact with one another, but still it's quite boring, because at the beginning of the universe, you have energy of photons. Those photons crystallize into, I suppose, what we would call a quark gluon plasma.
Mm-hmm.
That's really high energy. Then it falls down and you might make a proton and have some electrons. So then you can make hydrogen, and that's all you have. So me as a chemist, I'm like, you only give me hydrogen? What do I do with that? And then the nuclear physicist says, I'm going to take all this hydrogen with a bit of gravity, I'm going to produce some stars. So suddenly that hydrogen is compressed under gravity, starts to fuse, and you start to make heavy elements, and then it explodes, and you have all these other elements. You then have heavier elements still. So now you start to have a universe with stars in them burning, and some heavier elements. And as a chemist, I'm going around the periodic table going, cool, there's more stuff. And suddenly I have stuff, and what can happen when I have elements is they can start to make bonds. And when I start to make bonds, I start to get structures that didn't exist before, which kind of have stability. So that's where complexity is born, and it's kind of wild. You've got this chemist going, actually, all computer scientists, really smart mathematicians, Nobel Prize winners, all of you, you're all awesome, but actually, complexity starts with hydrogen in a star, and then let's go up from there. And is that controversial? I don't think so. It probably changes the discipline. Sorry.
Yeah, no, and I mean, is this seems like exactly that. It is your paper, the Nature paper on assembly theory. Is that essentially trying to explain and quantify that process? Is that a reasonable?
Yeah. I mean, and I think it says, look, and we had to work backwards in a way, because this way everyone's like kind of confused. It's called some cognitive dissonance in that assembly theory basically says there is causation at the base, right? So, and that causation acts, on things, right? And that causation isn't magic. Something has to cause that causation. So I would say that what assembly theory points to very concretely, it makes a proposal that selection can occur outside of biology. In fact, it had to. Otherwise, we have to invoke, a creator, right? So this is why the Nature paper, people say, oh, the paper's really controversial. I'm like, why? Is it controversial? Is there anything wrong with the science? They're like, no. Some people might not agree with the interpretation, but no one showed the mathematics isn't wrong. The hypothesis doesn't appear to be incorrect. People were just triggered by the fact that I said selection obviously had to predate biology, because selection is a more fundamental force in the universe. Now, force is probably the wrong word. It's a causal force, but perhaps, because forces in the universe are about fields, right? And a gravitational field, a electromagnetic field. In fact, gravity is special because it's not really quite a force. It's actually about a consequence of acceleration in space-time. But let's put that to one side. So selection has to provide a way for things to survive for some time, right? And in the end, the ultimate thing that selection has produced is free will. in fact, if you go all the way up, I don't know, the conversation probably won't be long enough. The pinnacle selection is that you and I can use our free will to decide not to walk across the road and get knocked over. Wait until the traffic light has changed. The bacteria, the lemming, the animal that doesn't understand our traffic convention, that can't do that. They just randomly run across the road. So actually, arguably, free will is the ultimate outcome of selection, because it enhances my ability to survive. And and free will and being curious is what we do when we're like playing around with the universe. Like, cats might play with each other and have fun and work, because the reason why they play with each other, if they got two little cats, and because they're preparing for finding a rodent and just playing around with that and capturing their prey, right? human beings being curious are basically and are when their needs are met, typically, or being pushed in one direction, can start to basically have new ideas, and those new ideas are interesting because they might lead to new technologies, new creative things, and they are selected on. Everything in the universe is selected, including free will, including the art. The ultimate reason for us being here is selection. The answer is selection is the force. It's like someone says, why does the sun exist? The answer is gravity. It's like, why does complexity exist? Answer, selection. And that's what that Nature paper said, and everyone went, what?
So let's step to this. So start at the beginning. What was the problem you were trying to solve with this paper or explore?
Yeah, I think that's a very important question. I think we go right back to the beginning because we started with the universe and ended up with free will in like 20 seconds, right? So I think, very simple question. As a chemist, I asked myself following about a decade ago. In fact, assembly theory was born when I was talking to my financial administrator 10 years ago, right? Who was, I realized that this guy has actually done a degree in mathematics and physics. I was like, why are you just doing my numbers? Surely we can have more fun than this. He was like, what? And I was like, so I actually got his PhD in assembly theory last year, which is kind of cool. So the question is this. If I find a molecule, like chemists play with molecules all the time, that's what we do. We either make them or we find them or we try and understand how they're created. So if I imagine I was like an astronaut and I went to the moon or Mars and I was able to find a molecule, the question I asked is really simple. How complicated, that's their word, complex or complicated, how complex does a molecule need to be before I can conclude that molecule had to be created, right? Had to have a creator. Or, that's kind of weird, like what do you mean by create? Well, I mean a cell, a person, whatever, so like technology. So that was my first question. And what I realized is that molecules can be cut up into smaller units and the complexity counted in some way using some experimental techniques. So I kind of invented the theory in my head using the experimental technique, which is a bit like, think of a molecule like a Lego object, and you smash it apart into the blocks and it can fall apart rather deterministically into the building blocks, or the smallest number of building blocks. So I asked myself that question, and that's where we started. And we started realizing that that living systems produce molecules of high complexity. Let's pause for a second. But I failed to mention the one other thing that was built into this, because everyone got really confused. I said, well, but surely random molecules could form. And surely random stuff could form. And I was talking to lots of experts in the complexity field, in the SFI, that's the Santa Fe Institute, in different institutes who were like being really nice to me, trying to help me understand things. And I realized that when as a chemist you detect a molecule, you can't detect a single molecule very easily. You have to detect a large number. And so what I was really telling everyone, say, hey, if I detect a large number of identical molecules that are complex, that tells me something interesting. And so I wrote a paper on this a few years ago, and we used this spectroscopy, and we basically said, look, it looks like all the molecules we have on planet Earth from biology can have high complexity from 1 all the way up to many hundreds. But non-biology, meteorites, and just random mixing can only make molecules that have a complexity or assembly index, which will up to 14. Anything above 14 or 15 or above can only be made by biology. And that's kind of where it started. So we had this process. We were making all these measurements in a lab. I built a theory that basically said, okay, I take my molecule, I cut my molecule up. What is the minimum number of ways of cutting up my molecule to get the assembly index? That's that number. The larger the larger the assembly index, the more steps required to make it, the more memory you need, right? Basically, the more lines of code you have to write down. But because I did it in a way that didn't require a conventional complexity compute process, it was more minimal, right? It got rid of this kind of whether I'd use a conventional complexity measure, like someone would say, how compressible is the molecule, or how much time would it take to make the molecule in a computer? How big would your molecule the program would be to make your molecule in a computer, because there was no computer, the origin. So that was where it started.
Yep.
And so let's recap. So I said that complex molecules found in high abundance cannot be made by chance. They have to be made by process. And then in the next step, and then with this Nature paper, we actually worked out, there's a process of selection that has to make these molecules, be it a cell, a human, a technology, and then the theory of assembly theory just backs all the way down and starts to build up and to explain those measurements and build a minimal infrastructure. That's why it's a theory, because the theory makes very concrete predictions and has an implementation that allows you to implement new experiments and thought experiments and simulation.
And so you're measuring the complexity of the object, and if you find enough of those objects, they couldn't have been made by chance. There has to be some process, and you're arguing that process is selection. And at some point, which I'd never heard before, which is really interesting, as that complexity grows, you sort of move naturally from chemistry to biology. Is that, which is a really interesting idea. That's really interesting.
I mean, I think that biology is a very special subset of chemistry that has survived selection processes, right? If you think about it, the chemistry in the cell is so intricate and complicated, and that had been selected through many processes. But what this paper does, it went, selection, it must be this process where there are random events, and if you make a random event, you take some building blocks and randomly create something. If there's no information, you're basically limited by how many steps you can take randomly, right, on it, because it's just a random walk. And then the environment will destroy it. So it's broken. So you're creating stuff, breaking stuff, creating stuff, breaking stuff, creating stuff, breaking stuff. So you've got the creation time, first time, and the breaking time. So you create and break, create and break, create and break.
Yep.
Now selection is like, if something is created randomly that somehow doesn't get eroded as quickly as its kin, if you like, or its siblings or whatever, other molecules, then there's some feature of that molecule that allows it to be resistant to decay in that environment. So that's the first step in selection. So now if that object can resist decay, it can out-survive some of the others, but that's not enough.
Okay,
that object that's created has to somehow act on the environment to cause more the production of itself. And what is implicit in assembly theory is that the unit of selection are causal graphs that intrinsically can self-replicate or get involved in a network of replicators in the environment to basically exist for a long period of time. Because, sorry.
So this is great. This is great, and this is where I get really confused. So if we go back just to joining atoms together and making molecules, is it fair to say that and let's say we start randomly, and we're going to end up with some of those molecules naturally more robust because of their bonds than others. So, like you say, they'll decay. They won't decay as quick, so they'll outlast. So this is the next step that you're going to that I find really difficult. I see how we got one. How do we end up with more than one of them? I mean, I can see how we could get it independently at a very simple molecular level that some things just join happily and some things don't. How do we get into that cycle where we end up with multiple copies of those that are somewhat not necessarily interconnected with each other, but at peace with their environment, should we say? That's probably a bad term, but more comfortable in their environment, that you get more than one of them?
So the more in the environment is a very interesting question. So what happens here, what the assembly paper does, it just basically says, look, we posit there's this thing called selection that can be quantified like this. Now here's a theory that explains how that should look like and makes predictions. And so now the environment imposes constraints on the molecules. Now Now let's imagine you've got lots of different environments, microenvironment. Environment one, and in that environment, you get one set of molecules that are formed. Another environment, another set of molecules. So this set of molecules is, let's say, molecules of class A from environment A are the ones that have come out, they survived. So the A stars have survived in the A environment, and the B stars have come in the B environment. But now suddenly the Bs get thrown into the A environment, and they're like, oh, shucks. They get killed. But not all of them get killed, and suddenly you get A and Bs in their each environments. They start to kind of mix traits because they interact with one another, and maybe an A molecule and a B molecule can join together randomly, and it has features to survive both an A environment and B environment. And so what you have is you build up this complexity, and it makes me kind of chuckle because the chemistry of the cell is horrendously complicated, but there's nothing more than a facsimile of the environment on Earth at the origin of life, and what the cell had to go through over countless cycles of replication and competition to get it right. It's a bit like if you imagine the perfect, I don't know, if you sail or ski or you do some physical activity and you want to have the right line and you can sail through the waves and you're perfect and you don't die. That's what the cell is. The cell has sailed through the waves and not died. But think of all the cells that have died on the way. Part of evolution, part of selection, that die. Only the thing that persists in time, it has survived that process. And so you've got this really strange thing that observation of objects that are complicated are very special. They have persisted in time and they've accrued this information. And it's a very complicated, it's a very complex dance, but it's actually very simple because you require the following elements. Random production of an object, the ability for the object to by chance survive in that environment. Then it has to be able to, but that's not enough. They die over time. Those objects have to also be able to act on the causal chain to amplify themselves. So it may not happen alone, it may be in a network. So when the ABs come together, maybe A and B can only get so far, but when ABs get together, they can make more ABs, and then, unnecessary baggage, they end up making C and D. And C and D are actually really quite interesting for survival, which help A and B. And then C and D are helped by A and B, but then they make E and F. And you keep going up and up and up, and you have this dependency of chemistry. And before you know it, you get metabolism, a genome, and a cell wall. And these are the things that basically are randomly required for any object to persist in time. And actually selection allows you to it's about survival bias. So when you see anything that's complicated, my new definition of complexity, complex objects or any complexity you see in the universe is a product of selection, survival, and self-replication, or a replication process, because nothing else would survive. The oldest objects on Earth are the ones produced by life, right? You know, some of the rocks are old, but they don't do anything. They're just hard, right? But they're weathered away. But the oldest artifacts on Earth are ones that have gone through evolution because they're constantly copying, rebuilding themselves.
So exactly on that, before we go to the cell, so the bit I struggle with here again is if we get an A and a B joined together and form a C, how does then that self-replicate? How does it make copies of itself, or is it making copies?
Yeah, it's not just it. So this is a very funny thing. It's what assembly theory kind of pulls out. So it's not just about. So I talked about in assembly theory, if you take a given object, a complex object, you can chop it into parts, right? The smallest set of parts required to make that object on a line, like we call it a graph, right? But it's like a chain of events. But it's not just the object that copies itself. In fact, the object is just actually proof that there was self-replication, because you've got loads of objects. It's actually the chain of events that is replicating itself.
Yes.
And that is just a really hard thing to get. So when you've got chains of events that can replicate themselves and you can pack them into a cell, suddenly you've got like a minimal factory that is autonomous. It can go from environment to environment. So it's very subtle and very interesting, But you're absolutely right. It's not the object that replicates. It's this chain of events that make the object.
Wow. So I mean, to put that in really simple terms, does that mean that it's not that we get an A and a B that join together to make a C, and then the C makes copies of itself? It's the fact that we had loads of A's and B's around anyway. When A and B got together, they survived. When we got our A's built and we got our B's built, and when A and B then got together and made a C, they just hung around because the other A's and B's sort of would have been, either dying out or joining together. So you end up with, so the multiple copies is important, not because something is copying itself. It's because the process through individual A's and B's was robust enough to work across a population, so to speak.
Yeah. The copy number totally gives you robustness. And it's kind of funny how it all plays together. So the nice thing about it is, like, assembly theory, it seems, for biology you need to add in a replicator from somewhere. Everyone's where the replicator comes from. In assembly theory, the replicators emerge as a function of assembly space. It's one of the predictions the theory makes, like how big does the tree have to be before self-replicators emerge, and we can now predict that and do those experiments, and that's pretty wild. And it's about kind of understanding the amount of time that's required, because an object that you have, a given object, tells you what the minimum amount of time required to make that object is, or the minimum number of events. That's probably better to say, because if you can have lots of compartments, you literally have more time. Because you have no compartment, you've got to do all those events in a linear way, right?
What do you mean by compartments? Is that like
a
different
cell.
environments?
Yeah, exactly, a microenvironment. So if you've got lots of microenvironments, and in each microenvironment you've got like the lottery being done, like the balls being pulled out. You could wait for the lottery once a week before you win the lottery, or you could have a billion lottery machines in their own environment, and you can play a billion. You've got your one set of numbers, and you can play them all at once. You'll win every time, right? So it's like so it's like time and space are interchangeable in selection and evolution, as long as you can have compartmentalization, enough energy and enough mass.
So we start to build up these more and more complex structures, and because we see lots of them, there's a high copy number in assembly theory language. We know that the process that built that is robust. And then do we get to this, and let's say we build up to the cell, is the key moment between non-life and life, and I'm sure we can talk about what we mean by that, this memory ability, this shift from the thing going, oh no, I actually can make a copy of myself now because I've got this genome inside me that has retained all that's good about me and can build me again. Is that the shifting point?
Yeah, I mean, I'm beginning to think that there was no origin of life, if you like, but I think that's probably not right. I think in the same way it's like saying there was no origin of the sun, because that's silly, because obviously there had to be a point where before the sun ignited, there was just hydrogen. It was getting hotter and hotter and hotter, but there was a point where the hydrogen got so hot under compression, under gravity, the nuclear fusion started, and nuclear fusion acted against gravity, so it blows up the sun. But when you've got enough mass to keep it in, you have this equilibrium, right? And then you do a phase transition. You go from. So I think the origin of life was a phase transition in copying and autonomy. So what I mean is, like, basically, for the origin of life to work, you have to be able to survive in lots of different environments. Because if you're not able to survive in lots of different environments, you aren't going to be able to really get a deep enough memory to survive. Because if the only thing that selection does is it builds configurations of matter that survive in the environment for long periods of time. And the way I put this in the Nature paper, we were very precise about this. We say, look, any object has a natural half-life where it could decay. In a molecule, what we mean by that is if we take a given molecule made out of, say, carbon and oxygen and nitrogen, that molecule in this average environment would start to degrade. It would just undergo side reactions, right? A bit like butter going off, or as it oxidizes, right? So you've got these background reactions going on. So what happens is you've got to compete against that that decomposition in the environment, and so that ever more elaborate process of selection that provides machinery, because now the cells, they don't just copy themselves, so don't just self-replicate. They have mechanisms to repair damage, repair DNA, deactivate, remove bad proteins and produce new ones. You've got all this complicated system that is basically centered on one thing, and that's the survival of the cell going forward, or the survival of the lineage. And so life, at the beginning, you have selection. So before life, I guess, you've got the beginnings of selection. And then when selection, it creates objects that are able to, or assembly spaces that are really robust, maybe on a planetary scale. I think Sarah's almost convinced me of that. I wasn't 100% sure why does its life need a planet, but I think she makes a very good point. And that's Sarah Walker, my collaborator at ASU, who said you've had on the podcast. That then life made in the UK could survive in Australia or Ireland or in New York, right? Because although the environments are slightly different, it's able to cope with it. And so, and as that goes forward in time, the more environments you have to cope with, literally the more memory you have to have, right? It's, new thing has happened here. Okay, we need to do this now. We need to switch this molecule to that molecule. We need to find a new source of energy, or we need to burn this, and so it's a bit like that. And so what I think is super interesting is that the assembly paper just says, hey, we know what the assembly index has been described before, but let's remind everyone what it is. But now there's this thing called copy number, which tells you about robustness. And then the assembly equation just says, hey, what is the amount of selection per unit volume, right? If you've got some stuff, and the assembly equation starts to point to that, right? And so the assembly equation is basically big A, that's the amount of assembly, is a function of the e to the power of AI, which is the assembly index, times the copy number minus 1 over the total number of objects, and you sum over all the different objects. And probably for the phase transition, the assembly equation needs a constant, but we weren't ready to put the constant in the equation because constants equal you're trying to fudge something. Well, in this case, we're not trying to fudge anything. What happens is you have a natural combinatorial explosion in chemistry where you just get lots of reactions, and the constant is needed, and the constant has units, right? Because you want to have the assembly per unit volume, per unit energy, right? Per unit time. So suddenly assembly is like a power density, or a power process where you're like the amount of assembly that's going on in the object in that volume. And so what we're beginning to do is understand that process now, and the next step is really to quantify volumes of the universe that are very good at assembling things versus others.